that last video, I think, right in the last minute. So that cutoff was a little bit rough. So I'll just kind of recap where I left off and then we'll keep going. This should be the end of all that stuff. What I had done right at the end there, if you remember, I took the derivative that you're seeing in this function right here. I'll highlight this little derivative we got from our model that we got from Excel. The derivative, which I'm putting an arrow on right now, is what we used in Excel to make these values called I guess it was MR, remember stands for marginal revenue, and so it's derivative of revenue for each value of Q, which is the number of the quantity of items produced. So if you look over here, there's a little formula that says negative 20 times B4, and that's this cell with 0 in it, plus 180, that's our derivative. And if you go down, it says B5, B6, and the cool way we can do that is you can take a formula and you can kind of copy and paste it down. And what it does is it thinks of any cell that I type in there. When I made this formula, I put the cell B4 in there, and it thinks of it as the cell 2 to the left. And so when I paste it, that's what it always says. Everything, calculate this with the cell 2 to the left. Do this with the cell 2 to the left. Do this with the cell 2 to the left. And you get all these answers. Well, those are our marginal revenue values. And over here, I plugged them into this table in our, the problem that we have says, please put in the marginal revenues from using the derivative. And so that's what I did. I plugged those in. And you notice I've got them in here in the table 180 when the quantity was 0, 140, 100, all the way down to negative 20. And then you're supposed to compare them to what was actually in the table that we were given from the beginning that you see up here, and they're pretty close. And the reason is a derivative gives you an idea of the rate of change if you know the actual rate of change from some real data that was taking place. They're going to be slightly off because we used a model equation to predict what was going on, then we took a derivative of it, so the derivative is also going to be a kind of a predictor, but less, just not precise, not exact. So that's the idea of modeling, is you're getting close, but not perfect, and that's okay, because we're just looking for a good idea. Now, as I cruise along, I think I'd finished up doing some derivatives here and some product rules and things like that. So to keep that going, I'm actually going to jump ahead. We're going to finish up the product rule, one little reminder on the product rule, and then we're going to do the quotient rule, and we're calling it good. It's a big day. So if you remember the product rule, if I take, what was this, question number 8 in our list of stuff, so if I do this problem right here, the way the product rule works is f prime of x, I'm going to go below the square first and then simplify. You always start with this template of, two derivatives, there are 2 things on the left plus 2 things on the right. There's always 4 components, and you separate by a plus sign. And what we do is we isolate and figure out what a first function would be. And so I think of that x being my first function, let's say, and then times a second function, let's say that green one I just highlighted would be my second function. And so if you look over here, I'm going to do the derivative of the first. That goes in that first block, so we call this the space for the d first, is what I like to think of. That'd be the derivative of x, which is 1. Okay, so I put it in there. And then this is d second in my mind, so I took the derivative of the I'm making this up. Wait, back up here. D first, I put it in here, which is x. The derivative of that is 1. The second unchanged, and I'm thinking through another operation here, but this is the second without touching it. So what happens is you only take the derivative of one of these components. There's a first function and a second function. You only do one at a time. Derivative of the first, second, don't touch it, plus the derivative of the second. Now that's 2x. Okay, the derivative of x squared plus 5 is 2x. So that's d second. And then the first unchanged. Boom. So if you notice, these 2 that are underlined are the first and the second function and the first function unchanged. I do take the derivative of each, but you do it in tandem with derivative of the first times the second unchanged plus the derivative of the second times the first unchanged. That's the product rule every single time. So I'll do a couple examples later on where we can use this in a different context. But that's it. I could write this in, and WebAssign would love it, but we always want to simplify a little bit. Like, for instance, I notice this will make x squared on the right-hand side, and then I've got an x squared. So altogether, I'd have 2x squared and an x squared. I'd probably write in 3x squared plus 5 in here, and that'd be my end result for my derivative. Okay, so that was a product rule from the other day. Quotient rule similarly has kind of a template for it. It's the derivative of each part at different times, just like the last one. So there's kind of a similar look to the product rule, but there's subtraction. Look at this. You know how the product rule is derivative of the first times the second unchanged plus That's a big deal right here. I'm going to highlight that plus. That's what the quotient rule is always talking about. There's a plus there. And then, but in the quotient rule, we're going to have this minus here, and that is a difference. Okay, we'll talk about the whole rule here in a minute. Over something squared, and I'll put what these are in here in a real low. There's a funny way to remember this that might help you. We think of this as the high function. We think of the bottom one as the low function. It's actually an easy way to remember this. And low as in, I'm putting LO, a terrible pronunciation, or I could put LOW if you like, but it goes low d high. You always start with the low, but not its derivative. D high means you take the derivative of the high function, and then minus, we actually say the word less. Okay, low d high less high d low over the square, so the over is the division sign here, over the square of low we go. So I'll walk you through it again with a little highlight here. Low d high less high d low over the square of low we go. And every time I say low, I'm referring to the bottom function. Whenever I say high, I'm talking about the top function. Now that's a funny mnemonic device. There's obviously a symbolic way you can do it with calculus, with f primes and g primes and things like that. But I like that method. It's kind of clean. It's easy enough to follow. Now we're going to put the actual low and high stuff in there. Now if you're interested, it might be good to kind of beforehand prepare yourself. I'm going to use, whenever I say high, I'm talking about x squared, the top, and whenever I say low, I mean x plus 5. If I want the derivatives of those, that's going to be 2x and 1 respectively. The derivative of x squared is 2x. The derivative of x plus 5 is 1. So keep an eye out for those, okay, as I do this. So our h prime will be our low, which was x plus 5, correct? Okay, and then d high comes next, and that's going to be where we do the 2x, the derivative of our top function. Okay, say 2x. There's an announcement for us. Low d high less high. The high function was x squared. D low, the derivative of the bottom, which is 1. Over the square of low we go. And our low, remember, is x plus 5 squared. So if I go back and do that little mnemonic device on top of here, remember here's low, d high, right here, the derivative of the top, less high, d low, over the square of low we go, low squared. Okay, so those are all the components. That's the quotient rule. That's the derivative of that quotient that we had in the beginning is done that way. Now you wonder where all these rules come from, who does this stuff. But there's wonderful proofs of that, and if you were taking Calc 1, Math 50, I would totally show it to you. But in our course, we're going to just go with those rules and understand that they have the same purpose. A derivative is still to find the slope of the tangent line for the original curve anywhere you want it. We use it the same way all the time. There's just different formulas for different types of functions. Obviously, there's a lot of simplifying. There's a lot of algebra that can happen in there. Hardest part of calculus is the algebra. This will work. This derivative that I have up here totally will work. But ideally, we would simplify it a little bit. We just kind of clean it up and do some just general stuff like on the top there. I would probably want to distribute the stuff in that first set of parentheses at least into 2x squared plus 10x, okay, from distributing the 2x to both of these terms. Okay, that's what I've got. And then the minus x squared times 1, I can just put minus x squared. And on the bottom, sometimes I don't usually distribute that. X plus 5 squared would be x plus 5 times x plus 5. It'd make x squared plus 10x plus 25 if you wanted to FOIL it out, but I wouldn't recommend it at this point. One last thing I might do is I probably combine like terms, that 2x squared minus x squared. So the best option I think I'd want to go for is it would simply become x squared plus 10. Remember, that's combining my x squareds here. X squared, 2x squared minus x squared, all over x plus 5 quantity squared. Okay, that'd be the derivative of that dude. And I could write any one of those 3 options you see on the right-hand side over there. So if I highlight all those in yellow here, there's 3 different versions of the derivative. They all would work in that situation. I'm going to choose the most simple of those if I were going to write it in here into this box. So I'd write x squared plus 10 over x plus 5 quantity squared. And that's just because I simplified it. You wouldn't want to make a rule like some shortcut to the quotient rule. Don't go for a shortcut. It is long. It takes all those steps, low d high less high d low over the square of low we go. Don't shortcut it in any way. You'll end up with something that's inaccurate. but you got to go through that process. The only reason it looks kind of similar to the original is after I simplified, it looks something like this. By the way, this is the whole thing I'm circling. That would be the result I'd write in there. Okay. One more quotient rule, and we'll call it good because the video is getting a bit long. If I do my g prime for this one of x, what I'm going to do is set up my template and put my 1, 2, 3, 4 sets of parentheses up top, minus in between. And down below I'm going to put my parentheses squared. And I'm just going to go in and write my low is you always start with your bottom function untouched in the quotient rule. And if you can remember that, order matters in the quotient rule, and it has to start with that low. And then d high is going to be just the derivative of 3x minus 6, which is 3. Less high, d low, so you take the high, 3x minus 6, put it in here. And the d low, the derivative of my bottom, is x squared minus 2. The derivative of x squared minus 2 would just be 2x. And then over the denominator squared, the low squared. And since I've already set up parentheses squared, I'm done. That's a perfectly good derivative. It'll do the job. It'll tell me the slope of the tangent line anywhere on that original g function. But it's a little clunky, so I would probably clean it up just a tad bit. Let me call it 3x squared to distribute the 3. Little things like that are always good, minus 6, and I'd probably distribute the 2x here on this one. And might want to notice that it is a minus that goes inside there. You're welcome to put that negative with the 2x, kind of rearrange these, turn them around. So there's some simplifying in there that I don't know how comfortable you are with, so I'll do it a step at a time. That'd make 6x squared minus 12x. Okay, that's on top over the x squared minus 2 quantity squared on the bottom. Now I'm noticing some like terms, and I want to really be careful that minus sign in the middle. So you be careful as well. And from a little bit of simplifying, I see x squareds here. That'd be 3x squared minus 6 squared, so negative 3x squared. I do see a minus and negative 12x, and so I should use a different color as I'm highlighting here. I see a minus a negative 12x, so you got to watch out for that as a positive 12x. And then at last is a minus 6 at the end over my regular x squared minus 2 squared. That's pretty good. I wouldn't go any further than that. That's what I'd plug in as my derivative. And voila, we're off and running. The rest of these are variations on those wonderful things. Number 12 you can do with the quotient rule, and you'd get a result. And number 13 you can do with the quotient rule as well. I'd challenge you to go and do that, but if you notice, there's actually a nice way to do it with algebra as well, but we can explore that later. So thanks for checking it out. We're going to move on.